imagine floating in the darkness far above our solar system, looking down at the slow spin of the planets below. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From that high and silent place, one world catches your eye above all others. It glows a soft, pale gold, and wrapped around its middle, catching the distant light of the sun, are rings so wide and so bright they seem almost too perfect to be real. That world is Saturn, and those rings have been astonishing people for a very long time. The story of how we found them begins in the summer of 1610. A man named Galileo Galilei pointed a small, handmade telescope at the night sky. Galileo had built one of the first telescopes ever used for astronomy, and he was sweeping it across the heavens, looking for anything new. When he found Saturn, something strange looked back at him. The planet did not appear alone. It seemed to have two round companions pressed close against its sides, one on each edge, like a planet with ears. Galileo had no word for what he was seeing. He had no frame of reference. He wrote in his notes that Saturn appeared to be made of three bodies, almost touching. He called it a triple planet. He had no idea he was looking at a ring system so vast it could swallow the distance from Earth to the moon and still have room left over. Then something even stranger happened. 2 years later, in 1612, Galileo looked again. The companions were gone. Saturn appeared perfectly round, alone, with nothing on its sides. He was baffled. He wondered if the planet had somehow swallowed its neighbors. What he did not know was that Earth had moved to a position where we were looking at Saturn's rings edge on. The rings are so incredibly thin compared to how wide they are that when viewed from the side, they nearly vanish. They become a thin, bright line, then almost nothing at all. The rings came back into view as the years passed, but it would take nearly half a century before anyone understood what they were actually seeing. In 1655, a Dutch astronomer named Christian Huygens turned a much better telescope toward Saturn. Huygens had ground his own lenses with great care, and his telescope was far more powerful than Galileo's had been. What he saw was clear enough to change everything. Saturn, he concluded, was surrounded by a flat, thin ring. A single solid disk, he believed, floating in space around the planet without touching it. He published his finding in a careful, coded message first, a common practice at the time to protect credit for a discovery, and then revealed it fully in 1659. Huygens was right that the rings were flat and that they surrounded Saturn without touching it. But he believed the ring was one solid structure, like a plate around a bowl. That idea would hold for more than 200 years. It was a Scottish scientist named James Clerk Maxwell who finally showed in 1859 that a solid ring could not survive. The forces of gravity would tear it apart. Maxwell worked through the mathematics carefully and concluded that the rings had to be made of countless separate small pieces, each one orbiting Saturn on its own path. He never saw this directly. He proved it with equations alone, and he was right. The final confirmation came from light itself. In 1895, an American astronomer named James Keeler used a technique called spectroscopy, which is the study of how light stretches or compresses depending on whether something is moving toward you or away from you. He measured the light coming from different parts of Saturn's rings and found that the inner edge of the rings moves faster than the outer edge. That is exactly what you would expect from millions of separate particles, each following their own orbit. A solid disk would spin at the same speed all the way across. The rings were not solid. They were a swarm. 4 centuries of looking, 4 centuries of wondering, and each generation got a little closer to the truth. Galileo saw something strange and could not name it. Huygens named it. Maxwell explained why it had to be what it was. Keeler proved it with starlight. And all of it, every question and every answer, was pointing toward something almost impossible to picture. A ring system so wide, so thin, so full of frozen light, that it remains one of the most beautiful sights in the known universe. So what exactly are the rings made of? After all those centuries of watching and wondering, the answer turned out to be something wonderfully simple. The rings are made almost entirely of ice. Water ice, the same stuff that forms forms on your windshield on a cold morning, or floats in a glass of water on a summer day. Frozen water drifting in orbit around a giant planet, hundreds of millions of miles from the sun, but not just a thin coating of frost. The rings are packed with it. Scientists estimate that roughly 90 to 95% of the ring material is water ice. The rest is rocky dust and trace amounts of other minerals, likely silicates, which are the same family of minerals that make up much of Earth's own crust. So, when you picture the rings of Saturn, picture something closer to a snowstorm than a rock pile, a vast, slow, silent snowstorm, frozen in orbit. The individual pieces of ice come in a huge range of sizes. Some are as small as a grain of sand. Others are as large as a house. A few are the size of a mountain. Most of the material, though, falls somewhere in between. Scientists think the average chunk is roughly the size of a snowball you might pack together in your backyard on a winter afternoon. Small, light, drifting, each one following its own quiet path around Saturn, pulled by gravity, nudged by its neighbors, tumbling slowly through the dark. These particles are not evenly spread. They clump together in some places and thin out in others. They collide gently, constantly, like bumper cars moving in slow motion. When two chunks of ice brush against each other, they do not shatter. They nudge. They drift apart. The collisions are so slow and gentle that scientists describe them as more like a soft settling than a crash. The whole system has a kind of patience to it. A slow, steady motion that has been going on for a very long time. One of the most striking things about the ice in Saturn's rings is how bright it is. Ice reflects light extremely well, and the rings are no exception. They reflect sunlight back into space with remarkable efficiency. Scientists measure this reflectivity using a scale called albedo, where 0 means a surface absorbs all light, and 1 means it reflects all light perfectly. Saturn's rings have an albedo of around 0.4 to 0.6, depending on the region, which means they reflect between 40 and 60% of the sunlight that hits them. That is why the rings look so vivid and white when you see them through a telescope. They are genuinely bright, genuinely luminous, catching the sun and sending it back toward you across the void. The total mass of all that ice and dust is enormous by human standards, but surprisingly modest by the standards of the solar system. Scientists estimate that if you gathered every particle in Saturn's rings and pressed it all together into a single ball, that ball would be roughly the size of the moon Mimas, one of Saturn's smaller moons, which is itself only about 246 miles across, smaller than the state of Texas. All those billions of glittering ice chunks spread across a ring system wider than the distance from Earth to the moon, and together they would fit inside something smaller than a mid-sized state. The rings look vast because they are spread so thin, not because they contain so much. That thinness is part of what makes the composition so remarkable. You have an enormous amount of space filled with a relatively small amount of material, and yet the result is one of the most visually striking structures in the solar system. It is a little like how a soap bubble can catch the light and shimmer with color, even though the film itself is almost impossibly thin. The rings work on a similar principle. Not dense, not heavy, but spread wide and catching the light just right. The ice itself is not perfectly clean. Over time, tiny particles of space dust have settled onto the ring material, giving some regions a faintly reddish or brownish tint. The outermost rings tend to look darker and dustier. The inner rings tend to look brighter and whiter. Each zone has its own character, its own texture, its own subtle color. Scientists are still working to understand exactly what contaminants are mixed into the ice and where they came from. What we do know is this: the rings of Saturn are, at their heart, a collection of frozen water. Simple, familiar, extraordinary. Ice, catching the light of a distant sun, orbiting a world of clouds and storms, in a silence so deep it is almost impossible to imagine. Now, here is something that will stay with you. Something that seems almost impossible when you first hear it. Those rings, which stretch outward for hundreds of thousands of kilometers, are extraordinarily thin. Not just thin in the way a piece of paper is thin. Thin in a way that has no real comparison in everyday life. rings of Saturn are, on average, only about 10 to 30 meters thick. Some regions may be as thin as a single-story building is tall. And yet, they spread across a distance wider than the space between Earth and the Moon. Think about that for a moment. If you could shrink Saturn's rings down to the size of a piece of paper, keeping the same proportions, that paper would be far thinner than a human hair. Far thinner, in fact, than almost anything we can see with our eyes. Scientists compare the rings to a sheet of paper that stretches the length of a football field. The rings are that flat, that precise, that impossibly narrow compared to their width. This thinness is not an accident. It is the result of physics working patiently over a very long time. When the ring particles first came together long ago, they were moving in all different directions. Some were tilted, some were angled. They bumped into each other again and again in slow and gentle collisions. Each collision took a little energy away from the vertical movement, the up and down motion, and left the horizontal movement, the sideways orbit, mostly intact. Over thousands and thousands of years, those collisions flattened the rings down. The particles settled into a single shared plane, like a crowd of people, all finding the same level floor to stand on. This process is called collisional flattening. It is the same basic process that shapes many flat, spinning structures in space. The rings of Saturn are a beautiful example of how order can emerge from chaos. Given enough time and enough small interactions, Saturn's own gravity helps hold this flat shape in place. The planet pulls on every ring particle, keeping them locked into their orbit. Any particle that strays too far above or below the ring plane gets pulled back. The system is self-correcting, self-organizing, always returning toward that impossibly thin, impossibly wide sheet of ice. There are places where the rings are a little thicker. Near the edges of certain rings, particles pile up slightly, like snow pushed to the side of a road. Some of these edge regions can reach heights of several kilometers. Scientists have spotted these low ridges using images from the Cassini spacecraft, which spent 13 years orbiting Saturn and sending back data that researchers are still studying today. These ridges are tiny compared to the width of the rings, but they stand out because everything else is so flat. The flatness also explains something wonderful about how the rings look from different angles. When Saturn's rings are tilted toward Earth, they blaze with reflected light and look wide and bright. But twice during Saturn's long year, which lasts about 29 Earth years, the rings turn edge-on to our view. When that happens, they nearly vanish. A structure that spans hundreds of thousands of kilometers becomes almost invisible, reduced to a thin line of light. Galileo noticed this in the early 1600s, though he did not fully understand what he was seeing. He thought Saturn had somehow lost its companions. That edge-on view is one of the most striking reminders of just how thin the rings truly are. Something so vast, so visually powerful, so unmistakable in photographs, can disappear almost entirely when seen from the wrong angle. It is a reminder that what we see depends entirely on where we stand. The thinness of the rings also tells us something about the nature of the material inside them. The particles are not clumped together in a thick cloud. They are sorted, settled, organized. They move in nearly perfect circles, each one following its own path at its own speed, rarely straying far from its neighbors. The whole system has a kind of quiet discipline to it, a precision that feels almost deliberate, even though it arose from nothing more than gravity and time and the slow mathematics of countless small collisions. There is something deeply calming about that image. Billions of pieces of ice, each one tumbling gently in the dark, each one held in place by forces it cannot feel or know, all of them together forming something so thin it can vanish from sight, and yet so wide it dwarfs the distance from here to the moon. Quiet, ordered, endlessly patient. And that width is something worth sitting with for a moment. The rings of Saturn stretch outward from the planet's cloud tops for an enormous distance. From the inner edge of the main ring system to the outer edge, the rings span roughly 282,000 kilometers. That number is hard to hold in your mind all at once. So here is a way to feel it. The moon sits about 384,000 kilometers from Earth. The rings of Saturn are nearly that wide. If you could lift the entire ring system off Saturn and set it down in space between our planet and our moon, it would almost fill that gap. Almost, but not quite. The moon would still be visible beyond the outer edge, but just barely. That is the scale we are talking about. Not a thin halo, not a modest band of glittering ice. A structure so wide it competes with the distance between worlds. And yet, as we just saw, all of that width is packed into a layer barely a kilometer thick in most places. The rings are like an enormous sheet of paper laid flat in space, impossibly wide, impossibly thin, both things at once. The material that makes up this vast sheet is not evenly spread. The rings are denser in some places and nearly empty in others. The main rings, the ones you see in photographs, contain the bulk of the material. Scientists estimate the total mass of all the rings combined is roughly equivalent to the mass of Mimas, one of Saturn's smaller moons. Mimas is about 400 kilometers across, so all of those billions of ice particles spread across nearly 282,000 kilometers of space add up to something roughly the size of a single small moon. The rings are wide, but they are not heavy. They are more like a whisper than a shout. The ice that makes up most of this material is not exotic or rare. It is water ice, the same substance that fills Earth's oceans and polar caps, the same ice that coats the surface of comets drifting through the outer solar system. Water is one of the most common molecules in the universe. Hydrogen and oxygen bond together easily, and they are two of the most abundant elements in existence. Wherever conditions allow, water forms. It coats the moons of Jupiter. It hides beneath the surface of Mars. It drifts through interstellar clouds in frozen crystals too small to see. The ice in Saturn's rings is part of that same ancient supply. Water that has existed in some form since the early days of the solar system. Some of the ring particles are nearly pure water ice, so clean and reflective that they bounce sunlight back into space with remarkable efficiency. This is part of why Saturn's rings are so bright. They act almost like mirrors, catching sunlight and throwing it back. when you look at Saturn through a telescope and the rings seem to glow, that glow is mostly reflected sunlight bouncing off billions of tiny ice surfaces all at once. Mixed into the ice are traces of other materials, rocky dust, silicate minerals, and small amounts of organic compounds, carbon-based molecules that form naturally throughout the cosmos. These trace materials give some parts of the rings a faint reddish or brownish tint when studied closely. The Cassini spacecraft, which spent 13 years orbiting Saturn, detected these subtle color differences across the ring system. What looks pure white from a distance reveals quiet complexity up close. Those silicate minerals are worth a moment of thought. Silicon and oxygen bonded together in tiny grains are among the most common solid materials in the solar system. They make up much of Earth's crust. They form the dust clouds where new stars are born. When a rocky body breaks apart, whether from a collision or from the slow pull of gravity, it leaves behind grains of this ancient mineral dust. Some of that dust has found its way into Saturn's rings, carried there by impacts or captured over long stretches of time. So the rings hold water ice born from the earliest chemistry of the solar system, and mineral dust that connects back to the same raw materials that built the planets. Everything in the rings has a history. Everything came from somewhere. The ice and the dust and the faint organic traces are not random. They are pieces of a much older story, gathered together by gravity and spread across nearly 300,000 kilometers of quiet space, wide enough to swallow the distance to the moon, light enough to weigh no more than a small moon, bright enough to glow in the dark, and made of the same simple ingredients that built the world beneath your feet. Saturn's rings do not form one single solid sheet. They are made of many separate rings, each with its own name, its own character, and its own place in the slow, ordered system that circles the planet. Scientists have named these rings using letters of the alphabet, but the letters do not go in order from A to G the way you might expect. They were named in the order they were discovered, not by their position. So the rings, from the innermost to the outermost, run D, C, B, A, F, G, and each one is different. Each one tells a different part of the story. The D ring sits closest to Saturn. It is the faintest of all the named rings, barely visible even to spacecraft cameras. It begins about 67,000 kilometers above Saturn's cloud tops and stretches outward from there. The D ring is made of very fine, thin material, more like a whisper of dust than a solid structure. Gravity from Saturn pulls hard on anything this close. The planet's immense weight tugs at every particle, keeping them in tight, fast orbits. Particles in the D ring circle Saturn in just a few hours. They move quickly because they are so close. The same way planets closer to the Sun move faster than planets farther away. Saturn's gravity is the engine driving all of this motion. Just beyond the D ring comes the C ring, sometimes called the crepe ring. It is wider than the D ring and slightly brighter, but still quite faint compared to the brilliant rings farther out. The C ring is made mostly of water ice mixed with darker, dusty material. That dark material absorbs sunlight rather than reflecting it, which is why the C ring looks dim and gray in photographs. The C ring spans roughly 17,500 kilometers in width. It is a broad, quiet region, but not an empty one. Within it, scientists have found narrow gaps and thin ringlets, small lanes where the material thins out or bunches together. These patterns are carved by gravity, shaped by the subtle pull of Saturn's moons working from far away. Then comes the B ring. This is the brightest, most massive ring in the entire system. It reflects sunlight so well that it almost seems to glow on its own. The B ring is densely packed with ice particles, some as fine as powder, others as large as a house. It stretches about 25,500 kilometers wide. The particles inside it are so tightly gathered that light cannot pass through in many places. Scientists call this optical depth, a measure of how much light a material blocks. Parts of the B ring have such high optical depth that they are essentially opaque, like frosted glass. The sheer weight of material in the B ring makes it the dominant feature of the entire ring system. Beyond the B ring, separated by a famous gap, lies the ring. The ring is slightly less bright than the B ring, but still brilliant and wide, spanning about 14,600 kilometers. It is also home to some of the most interesting gravitational effects in the whole system. Gravity from Saturn's moons creates waves inside the ring, rippling patterns that spread outward through the ice like sound waves moving through water. These waves are called density waves and bending waves, and they reveal just how alive and active the ring system truly is. The forces shaping the ring are not gentle. They are constant, invisible, and powerful. Farther out, the rings grow fainter and more spread out. The F ring is a narrow, bright strand that sits just beyond the outer edge of the ring. It is only a few hundred kilometers wide in places, thin as a thread compared to the broad rings inside it. Two small moons, Prometheus and Pandora, orbit on either side of the F ring, and their gravity keeps it from spreading apart. The G ring comes next, a faint and diffuse band of dust. It is so thin and spread out that it barely registers in most images. And finally, the E ring, the outermost of the named rings, is the widest and most diffuse of all. It stretches across hundreds of thousands of kilometers, a vast, pale blue haze of microscopic ice crystals. That blue tint comes from the tiny size of the particles, which scatter short wavelengths of light, the same way Earth's atmosphere scatters blue light across the sky. From D to E, the rings span an enormous range of character. Some are dense and bright. Some are faint and ghostly. Some are sculpted by moons. Some are held together by gravity alone. But all of them move together, circling Saturn in the same slow, ordered rhythm, shaped by the same invisible forces that have been at work for millions of years. Among all the features in Saturn's ring system, one stands apart. It is not a ring at all. It is an absence, a gap, a dark, empty band sitting between the bright B ring and the outer A ring, wide enough to swallow a small world whole. This is the Cassini division, and for centuries, it puzzled everyone who looked at it. Giovanni Cassini first spotted this gap in 1675, peering through a telescope in Paris. He saw the rings split into two distinct bands, with a dark line running between between them. At the time, no one knew what made it. It looked like a clean cut, as if someone had drawn a dark circle around Saturn with a steady hand. Cassini assumed it was simply empty space. He was mostly right, though the full story took 3 more centuries to understand. The Cassini division is roughly 4,800 kilometers wide. That number is hard to hold in your mind. So here is a way to feel it. The continental United States, from the Pacific coast to the Atlantic, spans about 4,500 kilometers. The Cassini division is wider than that. If you could lay the lower 48 states flat inside this gap, they would fit with room to spare. And yet, from Earth, this enormous space looks like a thin, dark line between 2 glowing bands. What makes the gap so striking is what surrounds it. The B ring, sitting just inside the division, is the brightest and most densely packed ring in the entire system. It is thick with billions of ice chunks, some the size of a house, others the size of a grain of sand, all crowded together and reflecting sunlight like a field of fresh snow. Then the division opens up and the brightness drops sharply. Then the ring begins again on the other side, dense and glowing. The Cassini division is not perfectly empty. Scientists have found faint bands of material inside it, thin rings of dust and small particles drifting through the gap. But compared to the rings on either side, it is nearly bare. The density of material there is far lower, like the difference between a crowded city street and a quiet country road at midnight. The reason for the gap comes down to gravity and to a moon called Mimas. Mimas is a small, icy moon of Saturn, about 400 kilometers across, with a giant crater on one side that makes it look startlingly like the Death Star from science fiction. Mimas orbits Saturn farther out, beyond the rings. But its gravity reaches inward, and it pulls on any particle sitting in a specific zone within the ring system. Here is the key. Any particle sitting in the Cassini division takes exactly half as long to orbit Saturn as Mimas does. This is called a resonance, a kind of gravitational rhythm where 2 objects keep meeting at the same point in their orbits, over and over again. Every time a particle in the division completes 2 laps around Saturn. Mimas completes exactly 1. They line up repeatedly, and each time they do, Mimas gives the particle a small gravitational tug. Over millions of years, those tiny tugs add up. They nudge the particles out of the division, clearing the gap the way a broom slowly sweeps dust to the edges of a room. This same kind of resonance appears throughout the solar system. It is the same force that creates gaps in the asteroid belt between Mars and Jupiter. It is the same principle that locks certain moons into fixed rhythms with their planets. Gravity does not just pull things together. It also sorts them, organizes them, clears space between them, and keeps the whole system running in a kind of deep, quiet order. The Cassini division, then, is not a flaw in the rings. It is a signature. It is the mark that Mimas has left on the ring system simply by existing, simply by orbiting where it orbits, doing what gravity does. A moon millions of kilometers away has shaped a gap 4,800 kilometers wide, just by the patient, invisible pull of its mass. There is something calming in that. The universe does not need to be loud or violent to make something remarkable. It only needs time. It only needs the steady, tireless work of gravity, pulling and nudging and sorting, year after year, orbit after orbit, until a dark and elegant gap appears in the middle of a glowing ring system, perfectly placed, perfectly wide, waiting for a man in Paris to look up through his telescope one night and notice that something was missing. So we have the gap. We have the dark, clean space that Mimas carved out with nothing but gravity and time. Now look a little closer at the rings themselves. Float above them just for a moment and imagine what you would actually see. The rings of Saturn are made almost entirely of ice. Not rock, not dust, not metal. Ice. Bright, white, reflective ice. If you could hover just above the B ring, the widest and brightest of them all, you would see something that looks almost like a field of fresh snow stretching out in every direction. The surface would shimmer. It would catch the distant sunlight and throw it back at you in cold, clean flashes. The rings are among the most reflective objects in the entire solar system, bouncing back nearly 80% of the sunlight touches them. But where did all that ice come from? Scientists believe most of it came from somewhere closer than you might expect. The leading theory is that the rings were born from objects that once orbited Saturn itself. Comets, small moons, or icy bodies that wandered too close to the planet long ago, when those objects crossed a certain invisible boundary near Saturn. The planet's gravity tore them apart. It pulled harder on the near side than the far side, stretching and breaking the object until it came apart entirely. What was once a single moon or comet became billions of smaller pieces. And those pieces, already rich in water ice, spread out into the flat, glittering disk we see today. This is why the rings are so pure, so white. The original objects that broke apart were mostly ice, not rock. Saturn's gravity sorted through the debris, and what remained was a ring system built almost entirely from frozen water. Some of the particles are as small as grains of sand. Others are as large as a house. A few are the size of a mountain. But nearly all of them are coated in ice, tumbling slowly in orbit, catching the light. If you could reach out and touch one of those particles, it would feel something like packed snow, cold and dense, slightly rough on the surface from billions of years of tiny collisions with other particles. The ice is not perfectly smooth. Up close, each chunk would have its own small craters, its own scratches, its own history written in the texture of its surface. The color from a distance is almost pure white, but not quite. Scientists studying the rings with instruments aboard the Cassini spacecraft found faint hints of color in the ice. The inner rings carry a slight reddish or brownish tint. This comes from tiny amounts of rocky material mixed into the ice and from organic compounds, which are carbon-based molecules that have drifted in from outside the ring system over millions of years. Micrometeorites, which are tiny dust-sized particles from space, rain down on the rings constantly and slowly stain the ice. The outer rings stay brighter and cleaner because they receive less of this contamination. So the rings are not perfectly uniform. They are layered with history. The whiter the ice, the newer or more protected it is. The darker patches tell you that something from the wider solar system has been slowly settling onto the surface, year after year, like dust settling on a windowsill. There is something deeply physical about imagining this. A ring system hundreds of thousands of kilometers wide, and yet the surface of each individual particle is being touched, changed, and slowly colored by the same dust that drifts through the entire solar system. The rings are not separate from the universe around them. They are part of it. They receive it. They record it. The ice itself is ancient. The water molecules locked inside each ring particle may have formed in the early solar system billions of years ago, when the sun was young and the planets were still taking shape. Water is one of the most common molecules in the universe. It forms easily in cold clouds of gas and dust between the stars. It rides inside comets and asteroids. It coats the surfaces of moons. And here, around Saturn, it gathered into something extraordinary, something visible from Earth with a small telescope, something that glows in the dark like a pale lantern hung around a giant planet. The ice came from the solar system itself. It was sorted and shaped by gravity, and now it drifts in silence. Billions of pieces of frozen water, catching the light of a star 1.4 billion kilometers away, shimmering quietly in the cold and the dark, as patient and still as anything in the universe. And yet, for all that ancient ice, scientists are not sure how old the rings themselves are. This is one of the great open questions in planetary science. The rings look young. They are bright and white and clean, like fresh snow. But the solar system is old, very old, about 4.6 billion years old, and something that has been sitting in space for 4.6 billion years should not look this clean. Space is full of dark dust. Over time, that dust coats everything it touches. It darkens surfaces. It stains them gray and brown. The moons of Saturn that sit outside the rings are dark and dirty, exactly as you would expect ancient objects to be. But the rings are still white, still bright, still gleaming. That brightness is a clue. Scientists use it like a clock. The technical word for how much light a surface reflects is albedo. A perfect mirror has an albedo of 1. Pure black has an albedo of 0. Saturn's rings have an albedo close to 1. They reflect almost all the light that hits them. That level of brightness suggests the ice has not had billions of years to collect dark dust. It suggests the rings may be much younger than the planet they circle. Some scientists believe the rings formed somewhere between 10 million and a few 100 million years ago in the long life of the solar system. That is recent. The dinosaurs were already gone from Earth by the time some estimates suggest the rings may have taken their current shape. That idea is strange and wonderful to sit with. Saturn itself is ancient, but its most famous feature might be surprisingly new. Other scientists are not so sure. They argue the rings could be older, perhaps as old as Saturn itself, but that the ice gets refreshed over time. New material falls in from passing comets or from Saturn's own moons. Fresh ice covers the old dark layers. The rings clean themselves. In a way, the way a snowfield looks new again after a fresh snowfall covers the gray slush underneath. Under this idea, the rings are ancient, but constantly renewed, their brightness maintained by a slow and steady supply of new material. The Cassini spacecraft, which orbited Saturn for 13 years before its mission ended in 2017, gathered data that many scientists read as support for the younger age. Cassini measured how much dark material was mixed into the rings. It measured the rate at which dust was falling in from outside. It calculated how long it would take for the rings to reach their current level of contamination. The numbers pointed toward a younger age, but the debate is not settled. Scientists are still studying Cassini's data today, still pulling new answers from the measurements that spacecraft made before it fell into Saturn's clouds. What makes this question so fascinating is what it means for the future. If the rings are young, they are also temporary. They will not last forever. The same forces that shaped them are slowly taking them apart. But that is a story for a little later. For now, think about what it means to look at something and not be able to tell how old it is. Humans do this with stars, with rocks, with fossils. We look at the universe and try to read its age from the clues it leaves behind. The rings of Saturn are a puzzle in that way. They hold their age quietly, not giving it up easily. Every measurement scientists take is like holding a piece of ice up to the light and trying to see how long it has been frozen. There is something humbling about that. The most recognizable feature in the solar system, the thing that makes Saturn instantly recognizable even to a child, is something we still do not fully understand. We do not know exactly when it formed. We do not know exactly how long it will last. We know it is made of ice and rock. We know gravity holds it in place. We know sunlight makes it glow. But its age, its true age, remains a quiet mystery sitting 1.4 billion kilometers away. And perhaps that is fitting. The universe does not always give up its secrets all at once. It offers clues. It invites patience. It rewards the kind of slow, careful attention that scientists bring to it year after year, measurement after measurement, question after question. The rings drift on, bright and cold and silent, keeping their age to themselves, glowing in the dark around a planet that has been there since the beginning, waiting for us to understand them a little better each time we look. Out among the cold and quiet of Saturn's rings, something small is keeping watch. They are called shepherd moons. They are tiny worlds, most of them no bigger than a city orbiting just at the edges of certain ring bands. And what they do is remarkable. They herd the ice. They keep the rings in line. Without them, some of Saturn's most precise and delicate ring edges would slowly blur and spread, dissolving into the dark like smoke in a breeze. The idea of a shepherd moon is simple once you see it. A small moon orbits just inside the outer edge of a ring. Another small moon orbits just outside that same edge. The gravity of the inner moon pulls the ring particles forward. The gravity of the outer moon pulls them back. Together, they squeeze the ring into a tight, clean band. The particles have nowhere to drift. They are held in place by two tiny gravitational hands, one on each side, steady and patient. Prometheus and Pandora are the most famous pair. They guard the F ring, one of Saturn's outermost and most active rings. Prometheus orbits just inside the F ring, and Pandora orbits just outside it. Between them, the F ring is kept surprisingly narrow. A bright, thin strand of ice and dust wrapped around Saturn like a thread. Without Prometheus and Pandora, that thread would unravel. But Prometheus does something else, too. Something that took scientists by surprise. As it orbits, Prometheus dips close to the F ring and pulls streamers of material out of it, like a finger dragging through sand. These streamers create dark channels in the ring, long, thin grooves that appear and then slowly fade as the ring material drifts back into place. Prometheus completes this cycle roughly every 19 days, the time it takes for the moon to lap the ring once. Every 19 days, a new set of channels appears. Every 19 days, the old ones fade. The F ring breathes in and out on a rhythm set by a moon, no bigger than a mountain range. This is the pulse that the directive asks us to notice. Everything here moves in cycles. The shepherd moon's orbit, the ring particles orbit, the channels form and vanish, the edges sharpen and blur and sharpen again. It is not chaos. It is a system of interlocking rhythms, each one tuned to the gravity of something nearby. Pan is another shepherd moon, and it lives inside the Encke gap, a clear division within Saturn's ring. Pan is shaped like a walnut, wide in the middle where ring material has settled onto it over millions of years, coating its equator in a thick ridge of dust and ice. Pan sweeps through the Encke gap like a slow broom, clearing the lane as it goes, keeping the gap open. Without Pan, the Encke gap would slowly fill back in. Scientists have found more than a dozen moons that play some version of this shepherding role. Some are large enough to see clearly. Others are so small they were only found because of the gaps and waves they leave behind in the ring material. A moon too small to photograph directly can still announce itself through the disturbance it creates. The way a boat announces itself through the wake it leaves on still water. Atlas is another small shepherd, guarding the outer edge of the ring. Like Pan, it has gathered ring material around its middle, giving it that same rounded, flattened shape. These moons are not just guards. They are also collectors. They accumulate the very material they are meant to contain. Over time, they grow slowly larger, grain by grain, flake by flake. There is something deeply orderly about all of this. The shepherd moons were not placed there by design. They formed through the same slow gravitational processes that built the rings themselves. And yet, they ended up in exactly the right positions to do exactly the right job. Gravity arranged them. Gravity keeps them there, and gravity working through them keeps the rings sharp and bright and structured. The rings do not hold their shape by accident. They hold their shape because small worlds are circling them, nudging them, pulling them, breathing in rhythm with them. Every clean edge in Saturn's ring system is a signature. It says, something is here, something small and steady and gravitationally faithful, doing its quiet work in the dark. The universe, it turns out, has a way of putting the right things in the right places, not through intention, through physics, through the patient arithmetic of gravity, working across millions of years until everything finds its place and stays there, circling and circling and circling. Gravity does not stop at the edges of the rings. It reaches outward across empty space, touching everything nearby, and everything nearby reaches back. Saturn's rings do not exist in isolation. They sit inside a busy neighborhood. Dozens of moons orbit Saturn at varying distances, and each one pulls on the rings in its own quiet way. Some of those moons are close enough to sculpt the rings directly. Others orbit much farther out, but even the distant ones leave their mark. Gravity is patient. It works across any distance, and it never stops. One of the most powerful forces shaping the rings comes from a process called orbital resonance. This is when two orbiting bodies fall into a repeating rhythm with each other. Imagine two people on swings. If one swings twice for every once the other swings, they will keep passing each other at the same point, over and over. Each time they pass, they give each other a small push. Those small pushes add up. Over thousands of years, they can carve gaps in solid rings. The moon Mimas creates one of the most famous examples of this. Mimas orbits Saturn farther out than the main rings. It is a small, battered moon, roughly 400 kilometers across, with a giant crater on one side that makes it look a little like a pale, frozen eye. Mimas and the ring particles in the Cassini division fall into a 2-to-1 resonance. For every one orbit Mimas completes, those ring particles orbit Saturn exactly twice. Every 2 orbits, those particles receive a small gravitational nudge from Mimas, always at the same point in their path. Over millions of years, those nudges pushed the particles away. They cleared a gap nearly 4,800 kilometers wide. The Cassini division, that dark band visible even through a small telescope on Earth, is the signature of Mimas, written in empty space. But Mimas is not alone in this work. The moon Janus shares a similar relationship with the outer edge of the ring, the bright outermost of the main rings. Janus and another moon called Epimetheus are locked in one of the strangest orbits in the solar system. They share almost the same orbital path around Saturn. Every 4 years, the inner moon catches up to the outer one. When they get close, they swap orbits. The inner becomes the outer. The outer becomes the inner. Then the cycle begins again. This slow, repeating exchange sends ripples through the ring edge nearby, keeping it crisp and defined. Farther out, beyond the main rings, lies a faint structure called the F ring. It is thin and braided, twisted into strands that seem to wrap around each other. 2 small moons, Prometheus and Pandora, flank it on either side. Scientists call them shepherd moons, as the previous section described. But their influence goes beyond simple herding. Prometheus, the inner shepherd, dips close to the F ring on each orbit. As it passes, its gravity pulls streamers of ring material outward, leaving dark channels in the ring's surface. These channels are temporary. The ring slowly fills them back in. But Prometheus returns again and again, carving new ones. The F ring is never quite the same twice. Even Saturn's larger moons, orbiting far beyond the rings, shape the system in subtle ways. Titan, Saturn's largest moon, is bigger than the planet Mercury. Its gravity stirs the outermost faint rings, the E ring and the G ring, influencing where particles drift and how long they stay. Titan is so massive that its gravitational reach extends across hundreds of thousands of kilometers. Nothing in Saturn's neighborhood escapes it entirely. What emerges from all of this is a picture of constant, invisible negotiation. Every moon pulls on the rings. Every ring particle responds. The gaps, the edges, the braids, the waves, none of them are accidents. They are the visible record of gravitational conversations happening across enormous distances, in slow motion, over geological time. The rings look still from Earth. They look like a frozen painting, a smooth disk of pale gold and white hanging in the dark. But they are not still. Every edge is vibrating. Every gap is being maintained. Every particle is in motion, responding to forces it cannot resist and cannot escape. Gravity wrote the rings into existence. Gravity holds them in place, and gravity, working through every moon in Saturn's crowded neighborhood, edits them constantly, shaping and reshaping them the way wind shapes sand dunes. Never finished, never the same, always in the process of becoming something slightly different from what they were the moment before. And yet, for all that motion, the rings hold a kind of quiet beauty that goes far deeper than their shape. Look closely enough, and the ice reveals something unexpected. The rings are not simply white. They carry color. Subtle, soft, almost shy, but real. The B ring, the brightest and most massive of all the rings, glows with a faint reddish-brown tint in certain wavelengths of light. Scientists believe this color comes from organic compounds, carbon-based molecules mixed into the ice. These molecules may have arrived on the backs of meteoroids, tiny space rocks that crashed into the ring particles over millions of years and left traces of themselves behind. The ice absorbed those traces. The color stayed. The ring, sitting just outside the Cassini division, shows a slightly different shade. It leans toward a cooler, bluer tone in some regions. This is partly because the ring is younger in places, with fresher, cleaner ice that has not yet collected as much of the dark material raining down from space. Fresh ice reflects light differently than old ice. It is brighter, crisper, more blue-white, like new snow compared to the gray slush at the edge of a road in late winter. The D ring, the innermost of all the named rings, is so faint it is nearly invisible. It barely catches the light at all. Scientists only confirmed its existence in 1979, when the Voyager 1 spacecraft flew close enough to detect it. Even then, it appeared as little more than a whisper of dim structure, a ghost ring clinging to the edge of Saturn's atmosphere. To see it at all required instruments far more sensitive than any human eye. The difference in color across the rings is not just beautiful, it is information. Each shade tells scientists something about where the material came from, how long it has been there, and what it has been through. The rings are, in a sense, a record written in light. Astronomers read that record carefully, using spectrometers, instruments that break light into its individual colors, the way a prism does, to decode what the ice is made of and where it has been. Some of the most striking color differences appear in the B ring's inner and outer regions. The inner B ring is redder. The outer B ring is whiter. The boundary between them is not sharp. It fades gradually, like a watercolor painting where one shade bleeds slowly into another. Scientists are still working to understand exactly why this gradient exists. It may have to do with the density of the ring material, or with the way sunlight strikes different regions at different angles, or with subtle differences in the size of the ice particles from one zone to the next. Particle size matters more than most people would expect. The smallest particles in the rings are roughly the size of a grain of smoke. The largest are the size of a house. Most fall somewhere in between, ranging from tiny grains to chunks the size of a car or a small building. These different sizes scatter light in different ways. Smaller particles tend to scatter blue light more efficiently. Larger particles reflect more evenly across all wavelengths. The mix of sizes in any given region shapes the color that region shows to the outside universe. There is something remarkable about the idea that a ring system hundreds of thousands of kilometers wide can carry color variations visible to a spacecraft's camera, that the ice is not simply ice, but ice with a history. Ice that has been struck by meteoroids, dusted with organic molecules, shaped by radiation from the sun, and sorted by gravity into regions of different sizes and densities. Every particle has been through something. Every shade of color is the result of that experience. The rings also change color slightly with the angle of the sun. When sunlight strikes them at a low angle near Saturn's equinoxes, the moments when the sun sits almost exactly above Saturn's equator, the rings cast long shadows across themselves. The colors shift. Structures that were invisible at other times become suddenly clear. Scientists have used these seasonal lighting changes to reveal features in the rings that would otherwise remain hidden, like the way a raking light across a painting can reveal the texture of brush strokes that were invisible before. What the rings show in their colors and their gradients and their subtle variations is that even ice can carry a story. Even something that looks simple from a distance holds layers of complexity up close. The rings are not a blank white disk. They are a record of everything that has touched them, everything that has passed through them, everything the solar system has thrown their way across an enormous stretch of time. And yet, for all that the rings have gathered and held across time, they are also letting go. Right now, as Saturn drifts through the cold dark of the outer solar system, its rings are slowly draining away. Scientists call this process ring rain. It is quiet. It is gradual, but it is real, and it is measurable, and it tells us something remarkable about the life of this place we find so beautiful. Here is how it works. The ice particles in the rings are not perfectly still. They are constantly being struck by tiny meteoroids, hit by ultraviolet light from the sun, and touched by the charged particles that flow through Saturn's magnetic field. That magnetic field is a vast, invisible force that wraps around the planet like a shell. When it interacts with the smallest, finest dust in the rings, something strange happens. The dust becomes electrically charged, and once it carries a charge, Saturn's gravity pulls it downward along the lines of the magnetic field, and it falls. It falls toward Saturn. The ice and dust drift down through the upper atmosphere in thin, invisible streams. They fall like the finest possible rain, too small to see, too spread out to feel. But scientists have measured it. Data from the Cassini spacecraft showed that this ring rain is depositing material into Saturn's atmosphere at a rate of several thousand pounds per second. That number is worth sitting with for a moment. Several thousand pounds of ice and dust every second, raining silently down from the rings into the planet below. When scientists first detected this, they found strange patterns in Saturn's upper atmosphere. There were bands where water and other molecules appeared in higher concentrations than expected. Those bands lined up almost exactly with the places where the magnetic field lines from the rings met the planet's surface. The rings were writing their signature into the atmosphere of Saturn itself. The connection between the rings and the planet is not just gravitational. It is chemical. Material flows between them constantly, invisibly, like a slow breath. What this means for the future of the rings is something scientists find both fascinating and a little melancholy. At the current rate of loss, the rings may be gone in roughly 100 million years. That sounds like an enormous stretch of time, and by human standards it is. But in the life of the solar system, which is already more than 4 billion years old, 100 million years is not so long. It is roughly the time since the dinosaurs disappeared from Earth. In cosmic terms, we are watching something in its final chapter. There is a quieter detail inside this fact. Scientists believe the rings may be even younger than the solar system itself, perhaps only a few 100 million years old. If that is true, then we are living in a rare window. The rings formed relatively recently, and they will be gone relatively soon. The billions of years before us passed without these rings. The billions of years after us will pass without them too. We happen to exist at the precise moment when Saturn wears them. That is a small, still thing to hold in your mind as you drift toward sleep. The ring rain also carries organic molecules, the carbon-based building blocks that appear throughout the solar system. These molecules fall into Saturn's atmosphere and mix with what is already there. Scientists are still studying what happens to them after that. But the idea that the rings are not just ice and rock, that they carry the chemical ingredients of something more complex, adds another layer to what the rings really are. Even the way the ring rain falls is not uniform. It is heavier in some places than others, shaped by the structure of Saturn's magnetic field and the density of the rings above. The rain falls in patterns. It has a geography. Scientists have mapped it, and what they found looks almost like a weather system, invisible and slow, but structured and real. The rings are not static. They breathe. They lose material to the planet below. They gain material from meteoroid impacts above, and they shift and flex under the pull of moons and gravity and sunlight. They are in motion in ways that take centuries or millennia to become visible. But the motion is there. The change is there. And the loss is there too, grain by grain, drop by drop, in the long, slow rain that falls between the rings and Saturn's clouds. What the rings are showing us in this quiet detail is that nothing in the universe holds its shape forever. Everything flows. Everything changes. And sometimes the most beautiful things are the ones that are already slowly saying goodbye. For a long time, we watched Saturn from far away. Galileo Galilei saw something strange through his small telescope in 1610. He noticed that Saturn looked different from the other planets. It seemed to have two round shapes on either side of it, like ears or handles on a jar. His telescope was not strong enough to show him what they really were. He thought Saturn might be three separate objects, close together. He wrote it down, puzzled, and moved on. It took another 50 years before the answer came. In 1659, a Dutch astronomer named Christian Huygens looked at Saturn through a much better telescope. He saw the truth. Those strange shapes were not separate objects. They were a flat ring, tilted at an angle, circling the planet. He published his finding carefully, and the world of science shifted. Saturn was not just a planet. It was a planet wearing something extraordinary, but knowing a ring existed and understanding what it was made of were two very different things. For the next 300 years, scientists studied Saturn from Earth and learned what they could. They found the gaps. They named the rings. They measured the angles. They watched Saturn move through its long orbit and saw the rings change their tilt as the years passed. They did all of this with light alone, the light that bounced off Saturn and traveled across hundreds of millions of miles to reach a lens on the ground. Then came the spacecraft. Pioneer 11 flew past Saturn in 1979. It was the first human-made object to visit the planet up close. It sent back images that were blurry by today's standards, but they were real. Saturn, enormous and golden, with its rings spread wide. Scientists looked at those pictures and felt something shift inside them. Voyager 1 followed in 1980, and Voyager 2 came in 1981. These two spacecraft revealed that the rings were not just a few simple bands. They were thousands of ringlets, each one distinct, packed together like the grooves on an old vinyl record. The rings had structure that no one had fully imagined from Earth. Still, the visits were brief. Each spacecraft flew past and kept going, out into the dark. They could not stay. They could not orbit. They could not watch the rings over time and see how they changed. That changed in 2004 when the Cassini spacecraft arrived at Saturn and did something no spacecraft had done before. It slowed down. It entered orbit. It stayed. Cassini was a joint mission built by NASA, the European Space Agency, and the Italian Space Agency. It carried 17 different scientific instruments. It was about the size of a school bus, and it spent 13 years circling Saturn, watching the planet and its rings from every angle, in every kind of light, through every season Saturn could offer. What Cassini found reshaped nearly everything scientists thought they knew. It measured the mass of the rings directly and found they were lighter than expected, which helped scientists estimate how young the rings might be. It watched the ring rain falling into Saturn's atmosphere in real time. It discovered that the rings were not uniform, but had waves and ripples caused by the gravity of moons, like the surface of a pond after a stone is dropped in. It found the spokes, those strange dark features that appear and vanish across the rings, and it watched them form and dissolve over time. Cassini also flew through the gap between the innermost ring and Saturn's cloud tops, a region no spacecraft had ever entered. Scientists called this the grand finale. They were not sure what Cassini would find there, or even if it would survive the passage. It did survive, and it found that the space between the rings and the planet was surprisingly clean and clear, almost empty of dust and debris. That finding changed the way scientists understood how the rings interact with Saturn itself. On September 15, 2017, Cassini ran out of fuel. Rather than risk it drifting and possibly contaminating one of Saturn's moons, mission controllers sent it into Saturn's atmosphere on purpose. It broke apart and burned up, becoming part of the planet it had spent 13 years studying. Scientists around the world watched the signal go quiet and felt the weight of that silence. But the data Cassini sent back will take decades to fully understand. Scientists are still working through it, still finding things hidden in the numbers. Every answer Cassini gave us opened a door to more questions. That is how discovery works. One careful look leads to another, and the universe keeps offering more than we thought was there. Among all the strange things Cassini confirmed about Saturn's rings, one stands apart. It is something scientists first spotted decades before Cassini ever launched. Something that made no sense under the rules of physics as they understood them. They called them spokes. Spokes are dark, shadowy features that appear inside the B ring, which is the brightest and widest of Saturn's main rings. They look remarkably like the spokes of a bicycle wheel. They stretch outward from somewhere near the center of the ring, fanning across the bright ice in long, dark bands. When Voyager 1 flew past Saturn in 1980 and sent back its first clear images, scientists saw the spokes and stopped. Nothing in their models predicted them. Nothing explained them. The rings were supposed to behave like a simple system of orbiting particles, each piece of ice and rock moving at its own speed based on how far it sat from Saturn. Spokes should not exist. Here is why they were so puzzling. In a ring system, particles closer to the planet orbit faster than particles farther away. This is a basic rule of gravity. If you drew a line across the ring, that line would quickly smear and blur as the inner particles raced ahead of the outer ones. Any dark feature should stretch and dissolve within minutes. But the spokes did not dissolve. They held their shape. They rotated together, almost as if the entire ring were a solid disk, spinning as one piece. That is not how gravity works. That is not how orbiting particles behave. Scientists were genuinely baffled. The leading explanation today involves something called electrostatic charging. Saturn is surrounded by an enormous magnetic field, one of the strongest of any planet in the solar system. That magnetic field carries electrical energy. When tiny dust grains inside the B-ring become electrically charged, they can be lifted slightly off the main ring plane. These charged grains no longer follow the normal rules of orbital motion. Instead, they get caught up in Saturn's magnetic field and rotate with it all together at the same rate. This creates the spoke pattern. The dark color comes from the angle of sunlight. When light hits these lifted dust grains from the side, they scatter the light differently than the surrounding ice does, making them appear dark against the bright ring below. What makes this even more remarkable is that the spokes are not permanent. They form and then fade. Scientists watching the rings over time noticed that spokes appear more often during certain periods and nearly vanish during others. The pattern seems to follow Saturn's seasons. Near Saturn's equinox, when the sun shines directly over the planet's equator, spokes become more active and more visible. When Saturn tilts away and the sun hits the rings at a steeper angle, the spokes quiet down. Scientists believe the amount of solar radiation reaching the ring particles affects how easily they become charged, which in turn affects how often spokes form. Cassini watched the spokes closely over many years. It caught them forming in real time, something Voyager never had the chance to do. A spoke can stretch across thousands of kilometers of ring in just a few minutes. Then, over the course of an hour or two, it fades back into the bright ring surface and disappears. The whole cycle, from formation to fading, happens faster than a weather system on Earth. And yet, it is driven by forces operating on a scale that dwarfs anything on our planet. There is something quietly astonishing about the spokes. They are a reminder that even a system that looks simple from a distance, a flat ring of ice and rock, can hold surprises that take decades to explain. Saturn's magnetic field, its seasons, its solar radiation, and the tiny charged grains inside its rings are all connected. Pull on one thread and the others respond. The spokes are not a flaw in the system. They are a signature of it, a visible mark left by invisible forces working together across enormous distances. Scientists still have open questions about the spokes. The exact mechanism of how individual grains become charged, and why some regions of the B ring produce spokes more readily than others, is still being studied. The data Cassini gathered is helping, but the full picture is not yet complete. That is not a failure. That is simply where the science stands right now, honest and unfinished, the way real science always is. The spokes are strange. They should not exist by simple logic. And yet there they are, dark and patient, sweeping across the brightest ring in the solar system, waiting for us to understand them a little better. Saturn, like Earth, has seasons. That might seem strange for a planet so far from the Sun. But Saturn tilts on its axis, just as Earth does. That tilt is about 27 degrees, slightly more than Earth's 23 degrees. And because of that tilt, as Saturn moves around the Sun, different parts of the planet and its rings receive more sunlight at different times. The seasons on Saturn are long and slow. One full trip around the Sun takes about 29 Earth years. So each season lasts roughly 7 years. Those long seasons do something remarkable to the rings. When Saturn's north pole tilts toward the Sun, the rings catch sunlight at a steep angle. They are lit up brightly, almost like a mirror catching a beam of light. The ice in the rings scatters that sunlight in all directions. From Earth, the rings look wide and vivid. The colors inside them, the faint golds and grays and pale blues, become easier to see. Then, slowly, Saturn moves to the other side of its orbit. The angle changes. The rings begin to tilt edge-on to the Sun. For a brief period, the rings nearly vanish from view. They are still there, of course, but they are so thin, just a few hundred meters from top to bottom, that when seen edge-on, they become almost invisible. Galileo saw this happen in the early 1600s. He could not explain it. He thought Saturn had somehow swallowed its companions. The changing angle of sunlight also changes the temperature inside the rings. This matters more than it might seem. The ring particles are mostly water ice. behaves differently depending on how warm or cold it is. When sunlight hits the rings at a steep angle during summer, the surface of each ice particle warms slightly. When the rings tilt away and receive less direct light, they cool down again. Scientists using the Cassini spacecraft measured these temperature changes directly. The difference is small, just a few degrees, but even a small shift in temperature changes how the ice reflects light, how particles clump together, and how the ring system looks from space. There is another seasonal effect that connects the rings to something much larger. During Saturn's equinox, the moment when the sun sits directly above Saturn's equator, the rings receive sunlight from almost exactly edge-on. This happens twice in each Saturnian year, roughly every 15 Earth years. During equinox, the rings cast almost no shadow on Saturn at all, and Saturn casts almost no shadow on the rings. The light falls flat and even. This is when scientists can see the rings in a completely different way. Features that are normally hidden by shadow suddenly become visible. Small bumps and waves in the rings, some of them hundreds of meters tall, stand out clearly because they cast long, thin shadows across the flat ring surface. The Cassini spacecraft was in orbit during Saturn's equinox in August 2009. The images it captured during that time revealed vertical structures inside the rings that no one had seen before. The sun's changing position also affects the spokes described in the previous section. Scientists noticed that spokes appear more often during certain seasons. Near equinox, when sunlight hits the rings at a low angle, spoke activity increases. The angle of the light seems to matter. It changes how solar radiation interacts with the charged dust grains that form the spokes. So the spokes, the seasons, the sunlight, and Saturn's magnetic field are all part of the same connected system, each one responding to the others in quiet, steady ways. Even the shepherd moons, those small worlds that guard the edges of certain rings, feel the pull of the seasons. Their orbits are stable over long periods, but the subtle pressure of sunlight, a force called radiation pressure, nudges them slightly over time. Nothing dramatic, nothing sudden, just a slow, patient influence. The sun reaching across hundreds of millions of miles to touch even the smallest pieces of this system. What is remarkable about all of this is how much one distant star can shape a world it never touches directly. The sun does not reach out and move the rings. It simply shines. And from that shining, seasons are born. From those seasons, temperatures shift. From those shifts, the ice changes, the spokes respond, the shadows lengthen and shorten, and the rings themselves seem to breathe in and out over the course of decades. Every part of the system listens to the sun. Every part adjusts. The rings of Saturn are not a frozen, static picture hanging in space. They are alive with change, patient and slow, moving to rhythms set in motion nearly 5 billion years ago. And yet, for all that we can see, some of the most remarkable things about Saturn's rings cannot be seen at all. They can only be heard, not with human ears, of course. Space is silent in the way we usually think of sound. There is no air out there to carry a vibration from one place to another. But scientists have another way of listening. They use radio waves, a kind of invisible energy that travels through space just as light does. And when the Cassini spacecraft turned its instruments toward Saturn's rings and listened in radio waves, what came back was extraordinary. Radio waves pass through the rings the way light passes through a window. Some of the waves slip through easily. Others are blocked. The difference between what goes in and what comes out tells scientists something very precise. The size of the particles inside. Tiny grains of ice block certain wavelengths. Larger chunks block others. By studying which waves pass through and which do not, scientists can read the rings almost like a doctor reads an X-ray, building a picture of what is hidden inside. What they found was a ring system far more layered and complex than anyone had imagined. The rings are not uniform. They are not one smooth sheet of ice spinning quietly in space. They are full of structure, full of variation, full of regions where particles clump together and regions where they spread thin. The radio data revealed gaps and waves and density changes that the human eye, even with the best telescope, could never detect on its own. One of the most striking discoveries from this kind of listening involves something called density waves. These are slow, spiraling ripples that move through the rings the way a gentle wave moves across the surface of a still pond. They are caused by the gravitational pull of Saturn's moons, tugging at the ring particles as they orbit. Each tug is tiny, but over thousands of orbits, those tiny tugs add up. They push particles together in some places and pull them apart in others, creating a pattern of compression and spacing that spirals outward through the ring. The radio data made these waves visible in a new way. Scientists could measure exactly how dense the rings became at the peak of each wave, and how thin they grew in the valleys between. From this, they could calculate the total mass of the rings with far greater accuracy than before, and the answer surprised them. The rings are lighter than expected. They contain less material than scientists once thought, which tells us something important. The rings are probably younger than Saturn itself, added to the system long after the planet formed. This is one of the ways that listening in radio waves changes our understanding. It does not just describe what the rings look like right now. It reaches back in time and tells us something about how they came to be. There is another kind of signal that Cassini detected, one that is even stranger and more wonderful. Saturn itself generates powerful radio emissions, bursts of radio energy that pulse out from the planet in a rhythm. Scientists call this signal Saturn kilometric radiation, a name that simply means radio waves of a certain length coming from Saturn. For decades, scientists believed this rhythm was tied directly to Saturn's rotation speed, the way a lighthouse beam sweeps around at a fixed rate. They thought it would give them a precise measurement of how fast Saturn spins, but the signal did not stay fixed. It shifted. The rhythm changed slightly between the time Voyager measured it in the 1980s and the time Cassini measured it decades later. The two spacecraft recorded different values. This was deeply puzzling. A planet cannot simply change how fast it rotates. Something else was happening. Scientists now believe the radio signal is tied not to the deep interior of Saturn, but to activity in its upper atmosphere magnetosphere, the region of magnetic influence that surrounds the planet. The rings sit inside that magnetosphere. They are bathed in it constantly, and the radio waves that pulse through that magnetic field interact with the ring particles in ways scientists are still working to understand. What this tells us is that Saturn's rings are not passive. They do not simply float in space, unchanged and unchanging. They are part of a living, shifting system, connected to the planet's magnetic field, shaped by its radio emissions, altered by the slow drift of density waves moving through them like breath. The rings listen to Saturn, and Saturn, in its own way, listens back. Now imagine standing on Saturn itself, not on solid ground the way you might stand on Earth, because Saturn has no solid surface to speak of. But picture yourself suspended somewhere in its upper clouds, looking up through the amber and gold haze of that vast atmosphere. What would you see above you? The rings would arch across the entire sky. They would stretch from one horizon to the other in a great curving band, impossibly wide, glowing with soft white and silver light. From that vantage point, the rings would not look like a flat disk the way they appear in photographs taken from far away. They would look like a ceiling, a bridge, something enormous and close, hanging over the whole world. The light that reaches the rings comes from the sun, which from Saturn's distance appears much smaller than it does from Earth. The sun is about 10 times farther from Saturn than it is from us. That means sunlight arrives at Saturn already dimmed, already softened, and yet the rings catch it beautifully. The billions of ice particles that make up the rings act like tiny mirrors. Each one tumbles slowly, reflecting light in slightly different directions. Together, they create a glow that is gentle and diffuse, like light scattered through frosted glass. From inside the ring plane, the view changes completely. Saturn's rings are extraordinarily thin. In most places, they are only about 30 to 300 feet thick, even though they stretch hundreds of thousands of miles wide. If you were positioned right at the level of the rings, looking outward through them, they would nearly vanish. They would become a thin, bright line, almost invisible, like the edge of a sheet of paper held up to the light. The rings only glory when seen from above or below at an angle. Saturn itself tilts on its axis about 27 degrees, which is close to Earth's own tilt of 23 degrees. Because of this tilt, the rings are not always aimed the same way toward the Sun. As Saturn moves through its long orbit, which takes about 29 Earth years to complete, the rings catch sunlight from different angles. Sometimes the Sun shines more on the northern face of the rings, sometimes more on the southern face. The light shifts slowly over years and decades, the way afternoon light shifts across a room as the hours pass. This changing angle creates something remarkable. The rings cast shadows onto Saturn's cloud tops. Long, curved shadows that sweep across the planet's surface like the shadow of a great wing. When the Sun is low relative to the ring plane, those shadows stretch far across Saturn's atmosphere, dark bands cutting through the amber glow. When the Sun is higher, the shadows shorten and pull back. Scientists watching Saturn through telescopes and through Cassini's cameras have tracked these shadows over time, and they reveal information about the height and structure of the rings themselves. The color of the rings, seen up close, is not simply white. The main rings glow with a warm, creamy tone, somewhere between white and pale gold. This comes partly from trace amounts of iron and organic material mixed into the ice. The B ring, the brightest and most dense of all the rings, reflects so much light that it can actually outshine Saturn's disk when the geometry is right. The fainter outer rings, like the F ring and the G ring, are darker and more diffuse, catching less light, almost ghostly at their edges. There is something called opposition surge, a brightening effect that happens when the Sun, Saturn, and a distant observer line up almost perfectly. In that alignment, the shadows that each ice particle normally casts on its neighbors disappear. Every particle is fully lit at once. The rings suddenly blaze with extra brightness, as if someone turned up the light from within. Cassini captured this effect in stunning detail, watching the rings flare and settle as the geometry shifted. Light does not just bounce off the rings, it passes through them too. The thinner, less dense parts of the rings allow sunlight to filter through, creating a translucent effect, like light through thin curtains. The denser regions block the light almost completely, casting true darkness behind them. All of this, the reflection, the shadow, the color, the surge and fade of brightness, is the rings speaking in the only language light knows. Every photon that touches those ice crystals carries information about what the rings are made of, how thick they are, how they move. The rings are not just beautiful to look at. They are a record written in light of everything that has shaped them. Saturn is not alone in wearing rings. Other worlds in our solar system carry them too, each one a quiet echo of the same forces that shaped Saturn's great bands of ice and dust. The rings speak in light, as we have seen, but they also speak in something else entirely. They speak in vibration, in wave, in the deep, slow language of sound. Sound cannot travel through the vacuum of space. There is no air to carry it, no medium to push the wave forward. But vibration is not the same as sound. Vibration can move through solid things, through magnetic fields, through charged particles streaming outward from the sun. Scientists have learned to listen to these vibrations. They convert them into audio frequencies that human ears can hear. What they have found is astonishing. Jupiter has rings. They are faint and dark, made mostly of tiny dust particles rather than bright ice. They were discovered in 1979 when the Voyager 1 spacecraft flew past and caught a glimpse of them backlit by the sun. Without that perfect angle of light, they would have stayed invisible for much longer. Jupiter's rings are thin and wispy, nothing like Saturn's grand structures. But they are real, and they follow the same rules. Gravity holds them in place. Moons shepherd their edges. The same forces that sculpt Saturn's rings are at work here, just quieter, just dimmer. Uranus has rings too. They were discovered in 1977, not by a spacecraft, but by astronomers watching Uranus pass in front of a distant star. As the planet moved, the starlight flickered and dimmed before the planet even blocked it. Then it flickered again on the other side. Those flickers were the rings, briefly blocking the star's light as they crossed in front of it. Uranus has 13 known rings. They are narrow and dark, made some of them are only a few kilometers wide. They sit in sharp, well-defined bands, separated by gaps that are still not fully understood. Neptune also has rings. They are incomplete in places, forming arcs rather than full circles. These arcs puzzled scientists for years. A ring should spread evenly around a planet over time. Gravity and the constant nudging of particles should smooth everything out. But Neptune's arcs hold their shape. Scientists believe that small moons nearby are trapping the material in place, using gravitational resonance, a kind of rhythmic pushing and pulling that keeps the particles clustered together. It is the same principle that creates gaps in Saturn's rings, but working in reverse, holding things together instead of pushing them apart. Now, back to the vibrations. The Voyager spacecraft carried instruments that could detect radio waves and plasma waves, the movements of charged particles in space. When Voyager flew through the ring systems of these outer planets, those instruments recorded something remarkable. The interactions between the rings, the magnetic fields of the planets, and the solar wind created patterns of electromagnetic energy. Scientists took those patterns and shifted them into the range of human hearing. The result was a kind of music, not music in the way we usually mean it, not melody or rhythm in any familiar sense, but tones, pulses, a low, resonant hum that rose and fell as the spacecraft moved through different regions of the ring system. Saturn's rings produce some of the most complex of these sounds. The density waves inside the rings, rippling patterns caused by the gravity of moons, create regular oscillations in the ring material. Those oscillations generate waves in Saturn's magnetic field. Those waves travel inward and interact with Saturn's upper atmosphere. Scientists have converted these signals into audio, and what they hear is something between a drone and a chorus. Deep tones layered over each other, shifting slowly, like the lowest notes of an organ played in a very large, very empty room. There is something quietly moving about this. The rings are not silent. They are not still. They are in constant motion, constantly vibrating, constantly sending out signals that carry the story of their structure and their age and their relationship with the planet they circle. we cannot hear them with our ears in space. But with the right instruments, the right translation, the rings have a voice. Every planet that carries rings is telling the same story in a slightly different way. Dust and ice and gravity and time. The same ingredients arranged differently, producing different structures, different sounds, different light. The universe uses a small set of tools and builds an enormous variety of worlds from them. Saturn's rings are the grandest version of something that turns out to be surprisingly common. Rings are not rare. They are simply one of the ways planets speak. And inside those rings, hidden within all that ice and dust, something unexpected lives. The rings of Saturn are not empty. They are not simply flat sheets of floating particles drifting in silence. Tucked within the bands of ice and rock are tiny worlds of their own. Scientists call them moonlets. They are small, irregular, and difficult to spot. But they are there, embedded in the rings like seeds pressed into snow. The Cassini spacecraft found them by looking for the shadows they cast. When a moonlet passes through the rings, it disturbs the particles around it. It pushes some outward and pulls others inward. This creates a small wave, a ripple in the ice that spreads away from the moonlet in both directions. From above, these ripples look like the wake behind a slow boat moving through still water. Cassini photographed hundreds of these wakes, each one pointed back to a moonlet too small to see directly. Some of these moonlets are only a few hundred meters across. That is smaller than many city blocks. Yet, even at that tiny size, they carry enough gravity to shape the material around them. They carve small channels in the rings. They create tiny gaps. They hold their own little neighborhoods of orbiting debris. The mathematics here is precise and elegant. The strength of a moonlet's gravity depends on its mass. Its mass depends on its size, and its size determines exactly how wide a channel it can carve and how far its influence reaches. These numbers connect to each other in clean, simple ratios that repeat throughout the solar system. One of the best examples lives in the B ring, the brightest and most dense of Saturn's rings. Scientists found a moonlet there that appears to be slowly gathering mass. Particles from the ring are sticking to it. It is growing, grain by grain, over millions of years. This is how moons are born, not in a single dramatic event, but slowly, quietly, through the patient accumulation of small things. The moonlet is doing what Saturn's larger moons once did long ago in the early solar system. It is a moon in the making. The F ring holds some of the most active moonlets of all. This ring is narrow and bright and twisted in places, braided into strands that cross and recross each other. The moonlets inside the F ring are constantly colliding with its particles. Each collision sends fresh material spraying outward in bright jets. Cassini captured images of these jets, thin white streaks fanning out from the ring's edge like sparks from a slow fire. The moonlets are not just living inside the ring. They are shaping it, disturbing it, keeping it in a state of constant, gentle chaos. There is a beautiful order underneath all of this apparent chaos. The orbits of the moonlets follow the same laws that govern every object in the solar system. A moonlet closer to Saturn moves faster. A moonlet farther out moves slower. This relationship between distance and speed was first described by the astronomer Johannes Kepler more than 400 years ago. He worked it out by studying the planets with no telescope, using only careful observation and mathematics. And the same ratio he discovered then, the same elegant proportion, holds true for a tiny moonlet embedded in Saturn's B ring today. The universe does not change its rules depending on the scale. This is one of the quieter wonders of astronomy. The same equation that describes Earth's orbit around the Sun also describes a moonlet the size of a stadium, drifting through a river of ice 200 million kilometers away. The numbers scale perfectly. They always have. They always will. Scientists estimate that there may be thousands of moonlets hidden inside Saturn's rings. Most are too small to detect directly. They reveal themselves only through the patterns they leave behind, the ripples, the gaps, the faint disturbances in the ice. Reading those patterns is like reading footprints in fresh snow. You cannot see the creature that made them, but you can measure the prints, calculate the weight, and know with confidence that something was there. Each moonlet is its own small world, following its own precise path, governed by numbers that have not changed since the solar system first took shape. They orbit in silence. They gather dust. They shape the rings around them with a gravity so gentle it can barely be measured, yet so consistent it carves channels that last for centuries. The rings are not just a backdrop. They are a neighborhood, and the moonlets inside them are quietly, patiently, going about the slow work of becoming something more. But becoming something more has its limits, and those limits are written into the physics of Saturn itself. There is a boundary that exists around every large body in space. It has no walls. You cannot see it. No instrument can point to it directly, but cross it in the wrong direction, and the consequences are absolute. Scientists call this boundary the Roche limit, named after the French astronomer Edouard Roche, who first described it in 1848. The Roche limit is the closest distance at which a moon can orbit a planet without being torn apart by that planet's gravity. Here is what that means in simple terms. Gravity does not pull on an object all at once. It pulls harder on the side of an object that is closer to the planet, and softer on the side that is farther away. For a small pebble, this difference is tiny, but for a large body like a moon, the difference is enormous. The near side gets pulled much harder than the far side. That uneven pull stretches the object. If the object is close enough to the planet, the stretching force becomes stronger than the object's own gravity holding it together. And then it breaks apart. Saturn's Roche limit sits at roughly 140,000 kilometers from the center of the planet. The main rings of Saturn spread from about 67,000 kilometers out to roughly 140,000 kilometers from Saturn's center. Almost perfectly inside that boundary. That is not a coincidence. The rings exist where they exist precisely because this is the zone where material cannot hold itself together into a moon. Every grain of ice, every boulder, every moonlet inside that boundary is being gently, constantly, invisibly pulled apart by Saturn's tidal forces. The stretching effect of uneven gravity across a wide body. This is why the rings never became a moon. The material was always there. The building blocks were present, but the planet's own gravity would not allow them to gather into something larger. Anytime particles drift too close together and begin to clump, Saturn's tidal forces tug at the clump, pulling the near side harder than the far side, slowly working it apart. The rings are frozen in a state of almost becoming, always on the edge of forming something, never quite allowed to. Step outside the Roche limit, and the rules change entirely. Beyond that invisible line, gravity can do its slow, patient work. Particles can stick together. Clumps can grow. Moons can form and hold their shape. Saturn's larger moons, Titan, Enceladus, Mimas, all orbit well beyond the Roche limit. They were able to grow because they were far enough away that Saturn's tidal forces could not tear them back apart. The precision of this is worth sitting with for a moment. The rings are not simply a random scattering of ice. They are the direct result of a gravitational boundary that was set the moment Saturn formed. Material that fell inside that boundary could never become a moon. Material that gathered outside it could. The line between ring and moon is drawn by physics, and physics does not negotiate. Scientists believe the material in the rings may have once been part of a moon, or perhaps several moons that wandered too close to Saturn long ago. Once inside the Roche limit, those bodies would have been slowly pulled apart, their ice and rock spreading into the flat, glittering disk we see today. The rings may be the remains of worlds that almost were, broken gently, not by violence, but by the quiet, relentless arithmetic of gravity. There is something deeply moving about that idea. The rings are not debris in the careless sense. They are material that tried to become something, came too close, and was held in this in-between state, neither moon nor empty space, but something stranger and more beautiful than either, a region where the planet's own nature prevents certain things from existing, and in doing so, creates something that nothing else in the solar system quite matches. The Roche limit is the same around every planet. Earth has one. Jupiter has one. Even our own moon creates a small Roche limit for the tiny particles that orbit it. The rule is universal. It applies everywhere gravity exists, which is everywhere in the universe. And yet, Saturn's ring vivid expression of that rule we have ever found. They are what happens when a planet's gravity is strong enough and the material plentiful enough to fill that forbidden zone completely. The rings are the shape of a boundary made visible. They are the outline of a force we cannot see, drawn in ice and light across the dark. The rings do not simply float above Saturn, untouched and separate. They reach down. They connect. Scientists have discovered that material from the rings actually falls into Saturn's atmosphere, drifting inward along invisible lines of magnetic force. This process is quiet and slow, but it is real, and it is changing both the rings and the planet itself in ways we are still working to understand. Saturn has a magnetic field, an invisible force that wraps around the entire planet like a great shell. That field stretches outward past the rings, and the tiny charged particles inside the rings, small grains of ice and dust that carry an electrical charge, follow those magnetic lines the way water follows a groove. They slide inward, they fall, and when they reach the upper atmosphere of Saturn, they enter it like a fine, cold mist. Scientists call this process ring rain. It was first suspected decades ago, but the Cassini spacecraft gave us our clearest look at it. Cassini flew between the rings and Saturn's cloud tops in its final months, passing through a region no spacecraft had ever entered before. What it found there surprised everyone. The material falling from the rings was more complex than expected. It was not just water ice. It contained organic compounds, tiny carbon-based molecules, the same kinds of building blocks found throughout the solar system. The rings were feeding Saturn something richer than anyone had guessed. What we still do not fully understand is how much this matters. Scientists are still calculating how much mass falls into Saturn each year, and the numbers are not small. Some estimates suggest that enough material falls inward to fill a large swimming pool every half hour. Over millions of years, that adds up to something significant. The rings are losing themselves slowly to the planet they orbit, and the planet is receiving them, absorbing them into its clouds, mixing them into its chemistry. This raises questions that remain open. Does the ring material change Saturn's atmosphere in measurable ways? Does it affect the colors we see in the cloud bands? Does it carry energy or heat into the upper atmosphere? The data from Cassini pointed toward yes, but the full picture is still being assembled. Teams of scientists are still working through the measurements, still building models, still testing ideas against what the spacecraft recorded in those final, extraordinary dives. There is also a deeper mystery. Saturn's upper atmosphere is hotter than it should be. This has puzzled scientists for a long time. The Sun is far away at Saturn's distance, and the heat it provides should not be enough to explain the temperatures measured high in the atmosphere. Something else is adding energy. Some researchers believe the falling ring material may be part of the answer. As it enters the atmosphere, it interacts with charged particles and magnetic forces, and that interaction may release heat. The rings may be warming the planet in a small but real way, simply by falling into it. We do not know this for certain. It is one of the open questions that makes Saturn such a rich place to study. Every answer the Cassini mission gave us seemed to open 2 more doors. The spacecraft is gone now, but the data it collected will take years, perhaps decades, to fully understand. Scientists are still finding new things inside the measurements it made. There is something wonderful about that. A machine that finished its work in 2017 is still teaching us things today. The rings it studied are still giving up their secrets, one careful calculation at a time. And there are questions we have not even fully formed yet. We do not know exactly how the ring material interacts with Saturn's moons as it drifts inward. We do not know whether the organic compounds falling into the atmosphere could play any role in the chemistry of the cloud layers far below. We do not know how this process has changed over time, whether it was faster in the past or slower, or whether it pulses and shifts with Saturn's seasons. These are not frustrating gaps. They are invitations. They are the places where the next discovery is waiting. Every unsolved question about Saturn's rings is a door left open. And somewhere, right now, a scientist is walking toward it. The rings have been visible in telescopes for 400 years. Spacecraft have studied them up close, and still they hold things we have not yet found. That is not a failure of science. That is science working exactly as it should, always finding that the universe is a little more intricate, a little more surprising than the last best answer we had. Right now, tonight, Saturn is up there. You may not be able to see it with your eyes alone, depending on where it sits in its orbit. But with even a small telescope, a modest backyard instrument, no bigger than a carry-on bag, you can see the rings. They appear as a soft golden oval around a pale cream-colored sphere. The sight is so striking that many people, seeing it for the first time, assume it must be a sticker on the lens. It looks too perfect, too neat, too much like a drawing someone made of what a planet should look like. But it is real. All of it is real. What you are seeing when you point that small telescope at the sky is a structure roughly 270,000 kilometers across. That is the full width of the ring system, from one outer edge to the other. And yet it is so thin, so impossibly flat, that from certain angles it nearly disappears. Twice during Saturn's 29-year orbit around the Sun, the rings tilt edge-on toward Earth. When that happens, the rings seem to vanish. The planet looks almost bare. Galileo saw this happen in 1612 and was deeply confused. He had noticed Saturn's strange shape years before, and then suddenly it was gone. He did not live to understand why. Right now, depending on the year you are listening, Saturn may be showing you its rings at a steep tilt, wide open and glowing. Or it may be offering only a thin silver line. The rings go through this cycle slowly, like a slow breath. Open, close, open again. Each tilt gives us a different view of the same ancient structure. From Earth, the rings glow with reflected sunlight. They are bright. In fact, the rings are among the most reflective surfaces in the solar system. The water ice that makes up most of the ring material reflects sunlight very efficiently. The way fresh snow on a clear morning catches the light and throws it back at you when Saturn is well placed in the night sky, it can outshine most stars. Ancient peoples noticed this wandering golden light long before anyone knew what it was. The rings also change color slightly depending on the angle of the sunlight. When the sun is low relative to the ring plane, the rings can take on a warmer, more amber tone. When lit more directly, they appear whiter, almost silver. The B ring, the brightest and densest of the main rings, often appears slightly more golden than the others, though a ring just outside it looks a touch cooler. These are subtle differences, but they are real, and they carry information about the size and composition of the particles in each band. From Earth, you cannot see the Cassini division with the naked eye, but a decent telescope will show it as a dark gap between the A and B rings. A thin, dark line, like a pencil mark, drawn carefully around the planet. That gap is roughly 4,800 kilometers wide. It is not truly empty, but it is sparse enough to look dark against the bright rings on either side. Saturn's rings are also tilted relative to Earth's sky. They do not sit flat like a coin on a table. They are inclined, angled, and as Saturn moves through its orbit, that angle shifts. Right now, the rings may be tipping toward you, showing their full face, or they may be tipping away. Either way, the view is worth finding. There is something quietly moving about the fact that you can see them at all. Those rings are made of ice and dust, shaped by gravity, sculpted by moons, slowly dissolving into Saturn's atmosphere. They are not permanent. They are not eternal. Scientists believe they may be gone in 100 million years, which sounds like a long time. But in the life of the solar system, it is a short season. We happen to live right now in this particular window of time when the rings are still there, still bright, still wide, still visible from a small blue planet circling a quiet star. That is not a small thing. The universe did not owe us this view. It did not arrange itself for our convenience. And yet here we are, at exactly the right moment, with the rings still intact, still glowing, still catching the light of our shared sun, and sending it back across hundreds of millions of kilometers to a lens, to an eye, to a quiet mind looking up at the sky on a clear night. The rings are there right now, turning slowly, waiting to be seen. The rings will not last forever. Scientists believe they are draining away, slowly but steadily, pulled down into Saturn's atmosphere as fine particles of ice and dust. The process is called ring rain. It is quiet and invisible to the naked eye, but it is real. At the current rate, researchers estimate the rings could be completely gone within 100 million years, perhaps even sooner. 100 million years sounds enormous, but the solar system is 4.5 billion years old. If you compressed that entire history into a single calendar year, the rings would vanish sometime in the last week of December. They are, in the grand story of our solar system, a brief and fragile feature. A season, not a permanent fixture. And yet here they are, still wide, still bright, still catching sunlight and scattering it in pale gold and silver arcs across the dark. There is something worth sitting within that fact. The rings exist right now, in this particular slice of cosmic time. Billions of years passed before they formed. Billions more will pass after they are gone. And we are here in the middle, in this narrow window, able to see them. That is not an accident of luck exactly, but it is a remarkable coincidence of timing. When the rings finally go, Saturn will not disappear. The planet will still be there, enormous and golden, circled by its many moons. It will still be the second largest planet in the solar system, still wrapped in bands of amber cloud, still spinning so fast that its equator bulges outward slightly, but it will look different, quieter perhaps, less adorned. Future eyes, if any exist to look, will see a plain planet where the rings once were. They may not even know what was lost. The ice will have fallen. The dust will have settled. The shepherd moons will still orbit, but they will have nothing left to guard. It is possible, scientists say, that new rings could form again someday if a moon drifts too close to Saturn and crosses the Roche limit, the invisible boundary where Saturn's gravity overpowers the moon's own structure. The moon could break apart. Its pieces would spread into a new ring system. The cycle could begin again. Destruction and creation, as they so often do in this universe, folding into each other. That is the deeper pattern here. Nothing in space is truly wasted. The ice in the rings came from somewhere. Perhaps a shattered moon, perhaps a comet, perhaps material left over from Saturn's own formation billions of years ago. When that ice falls into Saturn's atmosphere, it does not vanish. It becomes part of the planet. It joins the clouds. It mixes with hydrogen and helium and the complex chemistry of a gas giant's upper atmosphere. The rings do not die. They transform. This is how the universe works at every scale. Stars burn for billions of years, then collapse and scatter their atoms outward into space. Those atoms drift through the dark for millions of years, then slowly gather under gravity into new clouds, new disks, new planets. The iron in the Earth's core was forged inside a star that died before our sun was born. The oxygen in the air came from ancient oceans and ancient life. Everything we are, everything we see, has been something else before. The rings of Saturn are part of that same story. They are made of water ice, and water is one of the most common molecules in the universe. The hydrogen in that ice was born in the first few minutes after the Big Bang, nearly 14 billion years ago. The oxygen was forged inside a star. Those two atoms found each other, bonded, became water, drifted through space, gathered around a young gas giant, and eventually became the most beautiful ring system in the solar system. And now, on a clear night, from a small rocky planet 100 million kilometers away, a person can look up through a simple telescope and see them, pale and thin and impossibly far away, but there, real, made of ancient ice, shaped by gravity, thinning slowly with each passing year. The rings are not permanent, but they are here now. And the fact that we can see them, that we can understand them, that we can trace the atoms in that ice all the way back to the beginning of everything, that is one of the quieter wonders of being alive in this universe. The rings are turning right now, out past the dark, past the cold, past the distance that the mind can barely hold, slowly dissolving, still beautiful, still there. Saturn has been turning for a very long time, long before there were eyes to see it, long before there was a sun to light it. The atoms that make up that planet, its clouds, its storms, its rings, were scattered across a cold and quiet cloud of gas and dust billions of years ago. Then something nudged that cloud. Maybe a nearby star exploded. Maybe two clouds drifted together. Whatever the cause, the cloud began to spin. from that spinning, everything came. This is the story the rings tell, not just their own story, but the story of the whole solar system. Every piece of ice in those rings was once part of something else. A moon, perhaps. A comet that wandered too close. A loose collection of rock and frost that never quite became anything larger. Gravity pulled it apart. The pieces spread into a flat, glittering band. And there they stayed, held in place by the same forces that hold the planets in their paths. The same forces that keep the moon close to Earth. The same forces that shaped everything we have ever known. Gravity is not just a rule. It is the great organizer. It pulls dust into stars. It pulls stars into galaxies. It pulls ice into rings and holds those rings in their perfect, flat geometry. When you look at Saturn's rings, you are looking at gravity made visible. A force you cannot see, drawn in light and ice across 100,000 kilometers of space. The rings are also a record. Scientists can read them the way you might read rings in a very old tree. The gaps tell of moons that passed through long ago. The waves and ripples tell of gravitational tugs still happening right now. The color differences tell of different ages, different origins, different histories, all pressed together into one thin, shining structure. The rings remember things. They hold onto the past in ways that are quiet and patient and very, very old. And yet the rings are young by the universe's measure. They may have formed only a few 100 million years ago, long after the dinosaurs appeared on Earth. Before the rings existed, Saturn was just a pale, banded planet turning alone in the dark. The rings arrived later, a gift of collision and gravity, and they will not last forever. They are draining away slowly, pulled down into Saturn's atmosphere as fine, glittering rain. In another 100 million years or so, they may be gone entirely. Saturn will turn on, ringed no longer as if they were never there. But they are here now. That is the thing to hold on to. Right now, as you rest, Saturn is out there. It is past Mars, past the asteroid belt, past Jupiter's enormous shadow. It is turning slowly in the dark, its rings catching the distant light of the sun, glowing faintly gold and white. The shepherd moons are nudging the edges of the rings into their clean, sharp lines. The ring particles are bumping gently against each other, grinding slowly smaller with each passing century. The spokes are forming and fading in the B ring. The Cassini division is holding its wide, dark gap. Everything is moving. Everything is working. Everything is connected to everything else, the way it has always been. You are connected to it too. The calcium in your bones was made in a star. The iron in your blood came from a stellar explosion. The water in your body has been ocean and cloud and river and rain. You are not separate from the universe. You are made of it. You are a part of the same long, slow process that made Saturn's rings, that made the sun, that made the first light after the Big Bang. The universe is not a cold and empty place. It is full. It is busy with gravity and light and chemistry and time. And somewhere in all of that, on a small rocky planet wrapped in a thin blue atmosphere, you are lying still, breathing slowly, letting the day go quiet. The rings are turning out past the dark. The galaxy is turning above you, so slowly you cannot feel it. The earth is turning beneath you, steady and warm. And you are here, small and safe and held in a universe that has been building toward this moment for 14 billion years. Rest now. Everything is still. Everything is turning. Everything is well. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.